All right, last section of the chapter on, well, last section we're covering on motion of the center of mass. All right, so first things first. We're going to do this in one form, but it really applies to every form. We're going to go after it just with particle form. So RCM is equal to a sum over RIMI divided by the sum over the mass pieces. And this is basically just a sum of Ri times Mi over the total mass. If we take the derivative of this with respect to time, we're going to get the velocity of the center of mass. And the velocity of the center of mass is found as taking d by dt of this summation on the top, but the mass is constant, so we just have dr sub I dt mi over m total. Or the velocity of the center of mass is just the sum of the masses times the velocities divided by the total mass. We can do that again. We can take d by dt of VCM. That gives us the acceleration of the center of mass. And that ends up just looking like a sum of the individual accelerations times the masses divided by the total mass. Okay. So we have two equations here of note, one for VCM and one for ACM. We're going to think about that ACM1 a little bit. So if we take ACM and we multiply it by M total, that is just equal to a sum of all the individual accelerations times the individual masses. And it turns out that that is equal to the net force on all the masses. Okay, so that is another result, and that one we need to talk about. All right, what is this equation telling us? Well, if forces are only internal, then the sum of forces will be on third law pair forces exclusively. That means the net force is 0. The result is, for an object or a collection of objects, that experience no outside forces, the motion of the center of mass is constant, completely constant. That's kind of neat. That means if the object wasn't moving, then the center of mass never moves. Or I should say, if the objects weren't moving. Wrote that completely wrong. That means if the objects weren't moving, then the center of mass never moves. Interesting result. And it also means if a collection of objects is acted upon by an outside force, the center of mass, at least, moves in the way we've already described, in the chapters leading up to this point. So, as we move forward into the next couple chapters, we're going to get some different ways of thinking about things. We're going to get rotations of objects. But what we've already learned to this point is not useless, because the center of mass of that object or those objects will still continue to move in exactly the way as we've described in our forces chapters and energy chapters and everything that's come before. It's just that that motion now only applies to the center of mass of the system, and not necessarily to all of its pieces at the same time. Okay, let's see. I suppose there is one other thing I should talk about, and that has to do with the VCM equation. If we multiply m total over to the other side, you see that we get a result of mi times vi. Well, the sum of mi times vi is just the total of the momentum. So VCM times m total is just equal to the total momentum. And that on its own is also kind of a fun result, although we don't make quite as much hay of that as we do of other things. Okay, these different facts can be used to find lots of other things. If you want to find V center mass, it's pretty easy to calculate based on the velocities and the masses. Vice versa, VCM times the total mass is just equal to the total momentum of the system at whatever point, if the momentum's conserved, if there are no external forces. If there are external forces, you get an external impulse. You kind of have to go through this ACM stuff and think about what we just talked about with ACM times m total is equal to the net force. Yeah, that's about it. We'll try some practice problems at some point, and I think that'll give you a better idea of how all of this is going to work. And that will be it for this last section, so congrats, we've made it to the end of momentum. Next up, we get into rotations and things get a bit harder from there. So, see you in the next video sets.